Triple integrals in spherical coordinates. So previously we've discussed doing triple integrals in cylindrical coordinates, and when dealing with regions of integration that are spherical, it's a better idea to do integrals in spherical coordinates, especially if the integrand also gets much more simplified if we use spherical coordinates. So what are spherical coordinates? We have the point xyz in black there, and we could describe it instead in terms of three other variables: rho, which is the distance from the origin to the point. Okay, so please distinguish between rho here in spherical coordinates and r in cylindrical coordinates. In cylindrical coordinates, r was the distance from the z-axis. Here, rho is the distance from the origin to the point. We also have phi, which is called the polar angle, and it's the angle that the positive z-axis and this line here would make. Okay, so it's the angle between the positive z-axis and that line there. How you could think about phi is in terms of latitudes. Okay, that's one way to think about phi if we're taking a crude analogy with Earth. Okay, so phi would be the latitude and it would be measured from the North Pole down. Okay, so the equator would have a phi of pi over 2, 90 degrees, and the South Pole would have a phi of pi, or 180 degrees. And the third variable is theta, and theta is the angle from the positive x-axis to this line here. Okay, and that line, what you see here, is the projection down onto the xy plane. And you could think about theta, if you want to take the analogy with Earth, as longitudes rather than latitudes. Theta is also called the azimuthal angle. What you see here is the way to convert from rectangular coordinates, x, y, and z, to spherical coordinates. Of course, be careful when you deal with inverse trigonometric functions. And if you start with rho, phi, and theta, the spherical coordinates, and you want rectangular coordinates, here's the formula to use. Notice this rho sine phi. What is that rho sine phi? It is the length that the projection of this line that starts from the origin and goes to the point that we're considering. So if you look at the projection of that onto the xy plane, then rho sine phi is the length. Okay, and you could essentially prove that if you create a triangle here, where here you have 90 degrees, and so you could see that the distance away from the z-axis to the point is rho sine phi. Okay, if we were looking at cylindrical coordinates, rho sine phi would be equal to r. Okay, so rho sine phi is basically equal to the square root of x squared plus y squared. Rho is the square root of x squared plus y squared plus z squared. Okay, distance away from the origin. So this is a triple integral, and when we do triple integrals, we want to break up our region of integration into these 3D shapes. In rectangular coordinates, we would just use a rectangular prism and get the volume element that you see there. That's the small volume of a rectangle, of a rectangular prism. In spherical coordinates, we break up our region of integration into these spherical wedges, and here we have d rho. Okay, if this was a physical setting, rho would have a unit of length, so meter. Out here, this outer arc has a distance has a length of rho d phi. So this is the distance that one would walk as they're moving from the North Pole down to the south, okay? And so the length of that arc is rho d phi. And here, this length is rho sine phi d theta. And this is the length that one would walk as you're rotating about the North Pole. And why that sine phi shows up, again, it's the distance away. The closer we are to the North Pole, the easier or the shorter the distance to walk around the North Pole, okay? So if one was particularly lazy but still wanted to walk around the Earth in the sense of moving around all of its latitudes, well, they could just go up close to the North Pole and essentially just rotate, and they would make it around the Earth, right, in terms of latitude. So that's where that rho sine phi is coming from. It's basically telling us that the distances as we move along a latitude should be shorter the closer we move towards the North Pole. And what you see here is a nice visualization of the spherical wedges that we use for doing triple integrals in spherical coordinates. And it's clearer why that rho sine phi shows up as we move around a latitude, okay? So we could increase phi and move it up here. And you could see that the distances get smaller as we move up there. Whereas if we move down closer to the equator, we must travel longer distances for any given d theta. So for carrying out triple integrals in spherical coordinates, we use this theorem here. It gives us the change of variables for triple integrals in spherical coordinates. If d could be expressed in this way in spherical coordinates, okay? So that your rho is bounded between functions of phi and theta, okay? And phi is between a and b, and theta is between alpha and beta, then our triple integral is given here in spherical coordinates. Let's look at each component. Here, our integration bounds are obtained from using our description of the region of integration above. Notice here that for any x, we use rho sine phi cosine theta, which is the formula for x for converting from spherical coordinates to Cartesian or rectangular. So wherever one sees a x, they plug in this expression. Wherever one sees a y, they plug in this expression. And wherever one sees a z, they plug in this expression. And what is this part coming from? Well, that is the volume element that we obtained an expression for above. And of course, this expression is accurate in the limit that delta goes to 0, that these volumes become infinitesimal. So let's take a look at an example. Here we want to evaluate the triple integral that you see above. The region, though, is the first octant between two spheres of radius 1 and 2 centered at the origin. Something to notice, the region of integration is spherical. It's the region between two spheres of radius 1 and 2 contained in the first octant. And also, notice this integrand here. The integrand has x squared plus y squared plus z squared. Well, that's rho squared, okay? In spherical coordinates, this would be equal to rho squared. So both the integrand becomes simpler if we use spherical coordinates, and also the region of integration is spherical, so it would be a good idea to carry out this triple integral in spherical coordinates. And what you see here is the region of integration. You could see that it looks like an eighth of a hollowed out sphere, okay? And we could rotate this and see how it looks a little better. You could see here it's hollowed out. So this is because the region of integration is between rho equals 1 and rho equals 2. And we're only in the first octant, so that's expressed by using the bounds for phi from 0 to pi over 2. So going from if we let z be the North Pole, right? Going from the North Pole to the equator in the xy plane. And theta is also from 0 to pi over 2, from the positive x-axis to the y-axis there. What you're seeing there is our region of integration, not the function. The function would be expressed, say, in color, and if we let red be a lower value and blue be a higher value, then this sphere would get redder as you move out, okay? Because it goes like as we'll see, it goes as an inverse power of rho, and we'll see that. So let's go through the steps or ingredients for doing this triple integral in spherical coordinates. By now we should be getting used to these ingredients, as we've seen them a few times now. So the first ingredient is describing the region in spherical coordinates. So here we're only dealing with the first octant of a hollowed out sphere. Basically, the region is between two spheres of radius 1 and 2. And so rho is between 1 and 2. Phi is between 0 and pi over 2. And theta is between 0 and pi over 2. The second ingredient is converting the integrand above here, or the function, to spherical coordinates. So here's our function, which is the integrand above here. And how do we convert to spherical coordinates? Well, wherever we see a x, we plug in this expression. Wherever we see a y, we plug in that expression. And wherever we see a z, we plug in this expression here. And so doing so, we get this expression here. And what we could then do is we'll have a common rho squared sine squared phi in both of these first two terms, in the x squared plus y squared term there. And so you could factor out that common term and get cosine squared plus sine squared. Each of these depends on theta, so they have the same angle. And we could then use that this should be equal to 1. That's just a trigonometric identity. And so that's just 1. And then after getting 1 here, we could factor out the common rho squared between this term and that term. And so we'll get a sine squared phi plus cosine squared phi. So this time we have the same angle phi between these two. And so this is also 1. And this simplifies then to rho to the minus 3. And notice then that the function is decreasing as you move farther away from the origin. So if red had a lower value than blue, and we wanted to represent this function in 3 dimensions using color, this region of integration D would look redder as we move away from the origin. Okay, so we converted our function. What's ingredient 3 now? Ingredient 3 is using the volume element that we have above, over here, and that we looked at over here. So using that volume element in our formula above, so our triple integral now can be expressed in spherical coordinates this way. In blue, where did this come from? Well, it came from the blue ingredient, ingredient 1. Okay, these are all our bounds that we got as to describe our region. Rho minus 3, where did that come from? That's ingredient 2 after converting the function. And here is our volume element there. And we could then simplify, okay, and integrate. We'll integrate over rho first, although we can switch the order of integration here. But integrating over rho first, we get this expression, and plugging in the bounds into rho, since we just integrated over rho, we have this expression, and we could then simplify, and we do carrying out all of these steps, we end up with pi natural log of 2 over 2.